An S by R box, crafted by rows and columns. Inside, infinity. All right, so as we've seen in the last, oh man, how many lectures? I guess in the last 3 lectures. There is a wide variety, a perhaps surprisingly wide variety of real life, very interesting problems that can be condensed down to, that can be sort of like conceptually compressed into an analysis of a 2x2 table, or perhaps, right, if we want to take confounding or stratification into account, a set of such tables. However, right, it's still not hard to imagine or hard to think of more general, perhaps more nuanced situations where the response variable, the explanatory variable, perhaps both variables, end up taking more than 2 values. That is, certainly it's not hard to imagine situations that extend beyond a 2x2 framework. So here's 2 examples. First one is we might be interested in testing whether or not customer satisfaction, and we rate customer satisfaction as 4 possible categories: poor, fair, good, or excellent. We might be interested in whether or not that depends upon the type of customer service approach, right? And the approaches we're interested in are some sort of automated approach, or, right, a hands-on human approach. So think for a second, what would the size of that table be? What would the size of that table be? Yeah, perfect, right? That's going to be it's going to be a 2x4 table. Second bullet point, right? Here's what I meant by allowing like a little bit of nuance, right? Certainly, we might record someone's smoking habits as smoker and non-smoker, but it could be like there's more degrees in that, right? It's not necessarily quite so black and white, right? You could be like a non-smoker who has, right, for the most part, never smoked their entire lives. You could be a smoker, someone who's currently smoking right now, but you could also be maybe this third category, and this third category may or may not be relevant, or maybe you have spent a substantial amount of time smoking, but you quit a month ago or a year ago or 2 years ago, right? Maybe you spent more time smoking than not, but you still identify as a non-smoker. But like physiologically, the fact that you have smoked may or may not make a difference if we're talking about, right, some type of medical type study. And so in this example, I guess not a medical type study, we're interested in whether or not a person's smoking status, where we allow this kind of finer gradation of measuring that variable, might be useful in terms of predicting economic status, where we break economic status into 5 different groups. What would be the size of this table? Yeah, perfect. It's going to be a 3x5 table, right? So here we have examples of 2 right, real life situations that require us to move beyond our 2x2 framework. As powerful as that has proven to be able to pursue more interesting problems like this, we need to learn how to extend our methodology. Now, there's sort of 3 different approaches that we're going to take. Ah, man, I should have added my little cool checkmark symbol. I didn't even think about it till just now. But right, to finish off this particular PowerPoint, to finish off this lecture, right, these are the 3 things that we have to do. We're going to consider 3 different cases which give rise to 3 different approaches. We have the situation where both of our variables are nominal. Remember, nominal means that, right, the categories have no inherent ordering. We're going to consider the situation where one variable is ordinal and the other is nominal, right? So ordinal means they do have an inherent ordering. So one has an ordering, one doesn't. And then, right, the third situation is both of them have an inherent ordering. So, right, three different situations, each of which has three slightly different approaches to how we might analyze the data. Now, technically, in all three cases, at least kind of broadly, big picture, the null hypothesis is one of no association. So we're still kind of looking at, right, we have an x variable, we have a y variable. Are they related with one another? Are they associated with one another? It's just that, right, how we define this idea or notion of relationship is going to differ depending on which of those three situations we're in. It turns out that by using the extra information of ordering, if we have that, we can create and utilize more powerful tests, right? A more powerful test means that it has a higher probability of rejecting the null hypothesis when in fact the null hypothesis is true. Or sorry, when in fact the null hypothesis is false, my bad. Right, a more powerful test means a higher probability of rejecting H naught when we should be, right? When H naught is in fact false. So they're more powerful, and they also, right, consequently have less stringent sample size requirements. So here's our first case. This is case one. We're going to see it's something that we've kind of already been exposed to. And this is a situation where both of our variables are nominal. They do not have any type of inherent ordering. So our null hypothesis is no association between the two variables. Our alternative is that there is a general association between them. What do we mean by general association? General association in this case is defined as a heterogeneous pattern of distribution across the rows. That is, right, each row has its own probability distribution, and homogeneous pattern would mean that all the rows have the same probabilities. Heterogeneous means, right, at least two of those rows have a differing set of probabilities. Right, here's a graphical picture. Right, so these are the row percents. Those are typically what we're focused on. And our null hypothesis would be kind of like in this example of a 4x4 table. Our null hypothesis is actually, I don't know if we've seen this before or not, but it's kind of this like composite null hypothesis. It's kind of four parts to it. The first part is like all those probabilities in that first column are all equal to each other. Right, the probability of outcome 1, maybe the probability of getting an A, is the same regardless of which of those four groups you're in. And then, right, the second part of our kind of composite null hypothesis is that the probability of getting a B is the same for all four groups, and then the probability of getting a C is the same for all four groups, and the probability of getting a D or an F is the same for all four groups, right? So kind of our null hypothesis is that everything within a circle is equal to one another. And of course the alternative, right, symbolically would be that, right, there's at least one inequality somewhere within one of these circles. Maybe more inequalities and maybe more circles, but right, at least one circle has at least one inequality. Our test statistic is a very straightforward generalization of the Pearson's chi-squared test that we've already learned for a 2x2 table. So, right, all we do is we go to every one of our cells. We look at Nij, how many observations are actually observed in that cell. We compare that to Mij, how many do we expect to be there under a null hypothesis of independence or no association. Square that difference so that positives and negatives don't cancel. Divide that by what we expect. Here, that Mij, right, the expected cell count is still the same as before, still derived same as before. It's the row total times the column total over the overall total. And it turns out we can show mathematically that for a sufficiently large sample, this test statistic will follow a chi-squared distribution with S-1 times R-1 degrees of freedom. chi-square will follow, or this test statistic will follow chi-square, s minus 1 times r minus 1 degrees of freedom. Incidentally, do we see how the 2 by 2 Pearson that we've already learned is like a special case of this? Especially if we look at those degrees of freedom, right? Because if we have a 2 by 2 table, then our degrees of freedom are 2 minus 1 times 2 minus 1, so that's just 1 degree of freedom. Now, how do we define this idea of sufficiently large? Well, we define sufficiently large as a situation where all expected cell counts are 5 or higher. So same rule of thumb as we had in the 2 by 2 case as well. So this is a very straightforward generalization. Or, right, we might think of the 2 by 2 that we thought of as a special case of what we're talking about right now. Also, like before, our Pearson's chi-square test statistic has this sort of this Cochran-Mantel-Hansel, this randomization analog. Kind of comes about in the same way. That is, if we want to assume that margin totals are fixed, both row totals and column totals, this induces now a multivariate hypergeometric distribution. And then we can mathematically go from there to derive something called a randomization chi-square test statistic. We'll just call that Q. And actually it turns out that we have the same relationship that we had before. All right, that is, this randomization one is just a little bit smaller than the Pearson one, although very, very close. It also has the same formula for deriving the degrees of freedom. And incidentally, same rule of thumb for what is needed for it to be sufficiently large to have a close enough approximate chi-squared relationship that we're justified treating it as if it was in fact chi-squared. So how do we do this in SAS? We can get the Pearson's chi-squared statistic with just the chi-square option. We're familiar with that. And we can get the randomization chi-square by using the CMH option. We're also familiar with that. So the code is nothing new to us. All right, let's tackle an example. So this is I kind of modified the data set a little bit from a real life study from the year 2000, where 430 people were asked which medium they found the most credible in terms of reporting the news. And the people were asked from 3 different cities. So Los Angeles, New York City, and hey, right, our beloved homeland of Philadelphia. The 3 options for which they found most credible were newspaper, TV, and radio. Yeah, kind of an interesting question, right? I mean, this study was done in 2000, but right, I feel like a lot of the examples we've been talking about are reasonably topical, right? Because now there is like a lot of debate over what's credible, what's not credible, right? Mainstream media, right? It might be nice, I guess, an updated version of this study would include like maybe like newspaper, TV, radio, Facebook, Twitter. Maybe we collapse all that into some kind of social media category. But at least for the time being, we're going to have to deal with this somewhat older study. So there's the data set. All right, you can of course put that in yourself and play around with it. The actual code to analyze it's nothing new to us. We have a proc freq statement and that chi-square option and the CMH option. So here is our table. Right, we can look at it really quick. I'll ask some questions down in further slides, but right, we can see the chi-square test statistic, 4 degrees of freedom, right? That's because our table is what? Our table is 3 by 3. So the degrees of freedom are going to be 3 minus 1, which is 2, times 3 minus 1, which is also 2. 2 times 2 is 4. Our test statistic is 39.5914. That's our Pearson's. And so, right, the p-value associated with that is very, very, very small, less than 0.0001. It means that that there is a relationship, there is a difference in in media preference, or right in the media found most credible between at least two of these cities. Where do you think that difference lies? That is kind of one of the unfortunate things about the chi-square test. I mean, you can do follow-up tests where you do like maybe look at a 2x2 table or a 3x2 table. You kind of start looking at little segments of your table, but it's not very easy to do like a black and white objective follow-up test. What I've seen done more in practice is becomes a little bit more qualitative, where we say, okay, there is a difference. Let's look at that table and see if we can see what that difference is. And to me, the difference that really kind of sits out. So, right, we're comparing row percents, right? So where do we see the biggest difference in row percents? We see the biggest difference in row percents. It looks like all three cities kind of don't find radio that credible. They're all in that kind of 10-ish% range. The difference seems to be between paper and TV, and it's kind of most glaring what? It seems to be that LA seems to have a strong preference for TV as a credible news source. And New York City, right, it's kind of the flip of that, seems to look at newspaper as the most credible news source. So to me, that's the most striking difference. That's probably being observed by our significant test statistic. And then here, right, looking at our tables, this is the CMH table. The line that we're interested in is that general association line. We know that by the degrees of freedom, right? We know this test statistic is supposed to have 4 degrees of freedom. As anticipated, the test statistic is very, very, very close, but a smidge smaller. Same p-value, so same conclusion. So just kind of formalizing it, taking what I've just said, what I've just verbalized, and writing it down for us to see with our eyes. For those of us that are more visual learners than audible learners, our null hypothesis is that media preferences are the same for all 3 cities. The alternative is at least 2 cities have differing media preferences. Is a Pearson's chi-square test justified? Yes. If you go back to that table, you can look at all the expected cell counts, and all of them are in fact 5 or more. We already talked about this. Our test statistic was 39.5914. That was our Pearson's test statistic. Its degrees of freedom were 4. Its p-value was less than 0.001, so we would conclude that at least 2 cities have differing media preferences. Right, the most striking difference appears to be between LA and New York City. LA seems to have a strong preference, or a strong leaning towards thinking that TV is the most credible, whereas New York City seems to think that newspapers are the most credible. New York Times, I guess, right? And LA, of course, right? Hollywood and all of that. Makes sense that maybe they would have a different way of looking at, what's on our TV screen. Now, doing it by hand, right? Deriving that test statistic, that 39.5, whatever it was, would be a little laborious. But nonetheless, right, I put some of the terms up here just so we can see that it is just calculated the same way as we did it for our 2x2 table. Right? So there's 9 terms because there's 9 cells. That first term I took from the upper left-hand cell. So right, there were 30 people in that upper left-hand cell. We expected under the null hypothesis there to be 47.47 people. We take that difference, we square it. We divide by 47.47, do that for the next cell, and the next cell, and the next cell. My last term is the bottom right cell, in which there was 21 people. The expected cell count under the null hypothesis was 19.214, so we do 21 minus that squared over 19.214, and so I'll leave it to you to verify or not verify that that does in fact give us our test statistic. And then, right, we already pointed out, the randomization test comes from that general association line. It was a little bit smaller, but the p-value had the same bound. Question, if we measured the p-value very, very, very precisely, is a test statistic being a little bit smaller going to give us a larger or smaller p-value? Yeah, think about that for a second. If we measure it, so they're both less than 0.0001, so they're both technically, right, sort of imperceptibly small. But right, if we had a greater degree of perception, would the p-value for the randomization test be a little bit bigger or a little bit smaller? Good. It's going to be a little bit bigger, right? So that should make sense to us, regardless of whether we had 505 or not, right? Our p-value is the area to the right. So something that's a little bit smaller is going to have a little bit more area to the right, hence a little bit larger p-value. Ha! How is that? I have to admit, there have been a lot of growing pains. I cannot even begin to tell you how many times I've given a 3-hour, 4-hour lecture locked up in this little study that I put together here, this makeshift poor man's recording studio, and forgot to turn on the actual headset, forgot to set it up so it would actually record the 3 to 4 hours that I just jumped up and down and enthusiastically lectured myself hoarse. But I am learning. I am getting better. I'm starting to be able to figure out how to stop and start, and add little things like this. So, right, we were doing our lecture earlier. I wistfully thought, man, I wish I had thought to include some check marks into this PowerPoint. And then, boom, what'd I do? As if by magic, here they are. So the 3 things we need to do before this lecture is done. Both variables nominal, check. 1 variable ordinal and 1 nominal, soon to be checked. And then, of course, we'll wrap up by looking at the situation where both variables are ordinal. All right, so case 2. When we have 1 nominal variable and 1 ordinal variable, we try to set it up in such a way that our explanatory variable, our row variable, is the nominal one, and the response variable is the ordinal one. For what it's worth, this is what SAS expects. So if you're going to use the test that has 1 ordinal and 1 nominal, SAS is expecting your ordinal variable to be the columns. It's expecting your nominal one to be the rows. So the appropriate test for this situation is called the row means test. The row means test works like this. It creates these weights, referred to often by SAS and by the literature as scores, to the ordered outcomes of our ordinal variable. It uses these weights to create essentially these kind of categorical analogs to means. And so what we have then is we compute a mean for each of our rows and we compare those means. So what is that sort of analogous to? Right, whenever possible, as we're learning new material, right, we always want to try to, whenever possible, right, this is sort of educational scaffolding, if we can connect it to something that we've already learned or already mastered, it's going to make it easier for us to work through this new material. And so what is this sort of reminiscent of? It's reminiscent of like an ANOVA, right? It's like this categorical ANOVA that we're working on or computing. So let's dig more deeply into how SAS is actually calculating these means. It does it by assigning these weights. So how do we go about creating or assigning the weights? Well, I mean, there's more than two ways of doing it, but two of the more common ones are referred to as integer scoring, also referred to as table scoring. And the second one is referred to as standardized midranks, more commonly referred to as modified Ridits, or sometimes abbreviated as mod Ridits. Integer scoring is pretty straightforward. It assigns the weights 1, 2, 3, all the way to R to each of the R possible ordered outcomes. Right? So the weights are, in fact, right, these ordered integers. This type of scoring is encouraged anytime that we know the difference between each category is the same, right? So we would think of this as the categories being equally spaced. Now, usually for categories being equally spaced, it means that we actually are working with real numbers, because that's close to the only situation where this is going to be emphatically, right, without any reservation, without any argument, true. So maybe a situation where we have three types of pain relief, and we want to measure the hours of relief from pain symptoms, and the possibilities are 0, 1, or 2, right? These are measuring actual hours. So the difference between 0 and 1 hours is the same as the difference between 1 and 2 hours. We would say that there's equal spacing. Maybe we have 5 different products, and we measure the number of complaints regarding the product. And the number of complaints can range from 0, 1, 2, or 3. Maybe each product has like maybe 3 different aspects associated with it. And so, right, they could rate a problem in any one of these 3 aspects. So again, the difference between 0 complaints and 1 complaint is the same as between 2 complaints and 3 complaints. Again, an example of equal spacing. In a lot of other situations, and probably most situations, we don't have this idea of equal spacing, and so we would use something like standardized midranks. In this case, the weights are constrained to be between 0 and 1. They're assigned or created based on marginal column probabilities, right? So columns that have a lot of observations will be given more weight. The weights are also assigned in such a way that they are non-decreasing, right? Which makes sense. So we have these ordered variables, and larger right, quote, larger categories will have, right, larger, or at least not less in terms of weights. Using standardized midranks is encouraged anytime that we feel the difference between a category is not necessarily the same. That is, categories are not equally spaced, right? So I don't know. Think of like your Likert scale, right? Maybe you rate a particular political candidate, and maybe you like strongly approve, indifferent, disapprove, strongly disapprove, right? It's certainly not obvious, it's not clear cut, it's not black and white that the difference between like strongly approve and approve is the same as between indifferent and approve. That is, maybe it takes sort of very little for a candidate to kind of win us over, to move us from maybe our baseline indifference to saying, okay, fine, I approve. But maybe it takes a lot for that candidate to move us from approving them to strongly approving them, right? In most situations where we're dealing with abstract categories, where our categories are not actual numbers, the concept of equal spacing will not be clear cut, and so we probably will fall back on standardized midranks. Yeah, as I just implied. If you're not quite sure, you're like, I can kind of see it either way, then go ahead and use mod-riddeds. When in doubt, mod-ridded it out. So I already kind of sketched this idea, right? The basic idea is this. We essentially use these scores, these weights, to compute a mean, this kind of idea of like a generalized mean for each row. And then, much as we would in ANOVA, we compare the means to see how similar they are or are not. So here's the actual test statistics. The formulas look a little bit crazy. But I'll do a computational example and just a few slides that show that it's not quite that bad when you actually try to do it in practice. So what are we basically doing? This is actually very similar to ANOVA. So this is our book's notation. I'm not per se crazy about it. But that script F, that kind of cursive calligraphy looking F, sub I with a bar over it. So bar is like a mean, like X bar. That's our row means, right? So we have this script F bar for every row. We have a row mean. And kind of just like ANOVA, we're going to compare that to an overall mean. So we have this kind of mean for each group, right? Each row is like a group. And we compare that to the overall mean. That overall mean is kind of what we would expect under the null hypothesis of the means not being different. And so we want to see how different it is or isn't. So that, of course, is what feeds into our test statistic, right? The heart of our test statistic is that summation of that f sub I bar minus mu. It's basically what that test statistic is doing is it's comparing each row mean to the overall mean and seeing how different it is or isn't, right? If all the rows have the same mean, then that mean is going to be close to the overall mean. And if instead, right, the rows have different means, then of course, right, they're going to be kind of spread out all over the place. So at least some of them are going to be, right, far from that overall mean, which will give rise to a larger test statistic. So we can see intuitively, the larger that test statistic, the stronger the evidence that these row means are different from one another. Now, we can show that for a sufficiently large sample, this test statistic, this Q sub S, S is in row mean score, follows a chi-square distribution with S minus 1 degrees of freedom, right? So S is our number of rows. So here's an example. I'm not going to go all the way with it. I just want to use this example to kind of like show how those formulas work. So again, if you haven't already, it might be worth printing up that slide that has the formulas so you can compare it to what I do in just a couple slides. So we asked 22 independent voters what their opinion was of Bill Clinton's presidency. And there's 5 positives and 9 neutrals and 8 negatives. And then we asked 25 independent voters what their opinion was of Obama's presidency. And we get 6 positives and 10 neutrals and 9 negatives. So here's our table. 2 by 3. This is the type of situation where we would use a row mean score. Right, name of president is not necessarily ordered, so we could think of that as nominal. However, our opinion does have this gradation, right? A neutral opinion is better than a negative opinion. A positive opinion is better than a neutral opinion. So our columns are ordinal, our rows are nominal. So this is a type of situation where a row mean score test would be appropriate. So is the row mean score test? Yes, we just said rows are nominal, columns are ordinal. Now, of course, also part of what's appropriate is that sample size. We said only if it's sufficiently large. We have yet to talk about the notion of sufficiently large. We'll do that We'll talk about that soon. So again, you're going to have to go back and look at that formula and hopefully see where I got these numbers from. But the row mean for the first row, and here I'm leaving those A1, A2, A3, those are our weights, right? So if we were using integer scoring, which I would not recommend for this, right? A1 would be 1, A2 would be 2, A3 would be 3. Instead, I would recommend using modified Ridditt's, and so now these A's are going to be weights between 0 and 1, where A1 is smaller than A2 and A2 is smaller than A3. And what are we basically doing? If you actually look, I mean, it's actually pretty intuitive. If you look back, what's that 8 out of 22? It's the proportion of the people asked about Clinton. 8 out of 22 of them had a negative opinion. So it's the percentage of people that had a negative opinion times the weight for the negative opinion, plus the percentage of people that had a neutral opinion times the weight for a neutral opinion, plus the number of people that had a positive opinion times the weight for a positive opinion. And that's going to give us the mean score. And then we do that for the second row, same idea, right? This is the percentage of people, right, out of 25. 25 was the number of people that were asked about Obama. Of the 25 asked about Obama, 9 had a negative opinion. So we have 9 out of 25 times whatever the weight is for a negative opinion. And then we compare it to the overall mean. The overall mean looks at the column totals, right? So here it's basically saying out of all 47 people that we asked this question to, 17 out of them had a negative opinion. Out of all 47 people that we sampled, 19 of them had a neutral opinion. Out of all 47 that we sampled, 11 of them had a positive opinion. And then we go from there, right? So that's where those things are calculated. As you can see, sometimes looking at those formulas, like with their abstract notation, can sometimes feel a little daunting. But sometimes just grabbing a table and putting some numbers in there, right, makes it a lot smoother. Now, what do we mean by sufficiently large? So first, we would use the row mean score test whenever the columns are ordered and the rows are not, but we also need a sufficiently large sample size to justify using our chi-squared approximation. There's two things that we need, and we need both of these two. The second one's easy. We need the row totals to be 20 or more. The first bullet point is, again, it's one of those things where the concept is actually not that hard, but trying to actually write that concept out symbolically is a bit challenging. So the sample is sufficiently large if there exists some cut point such that if we add the first through j columns and the j plus 1 through r columns together, then we get 5 or more observations in all of our cells. So the idea is that you collapse the table together. You collapse the columns together. So there's a lot of different ways of collapsing columns together, and you're collapsing them in such a way that you're left with a 2 by 2 table. Or sorry, you still keep the number of rows. So you're collapsing it in such a way that you have a S by 2 table. So imagine 4 columns. Like, what are the possible ways we might collapse that? We can collapse the second, third, and fourth columns together. So we have the first column and 2, 3, and 4 together. We can collapse columns 1 and 2 and 3 and 4 together. Or, right, we can collapse columns 1, 2, 3 together and then also have column 4. So the idea is we're collapsing these columns, and if there exists a way to collapse them, so all of the cells in our now skinnier table have 5 or more observations, then our sample size is sufficiently large. So how do we do this in SAS? Very easy. We can get the row mean score test statistic and its p-value through the CMH option. Now, the default weighting, the default scoring in SAS is integer scoring. SAS will call this table scoring. If you want to change it to mod-ridits, then you have to use the score option and write score equals mod-ridits. And you do that in the table statement. Now, when you're doing this type of table, you must be cognizant of the ordering of your categories, right? That is, if you have a variable that is ordered, like negative, neutral, positive, you need to make sure that your columns are ordered correctly. That is, they are not ordered neutral, positive, negative. If you order your columns wrong, you are screwing up your analysis. The ordering doesn't necessarily matter for nominal variables, but if it's an ordinal variable and you are using a technique that exploits that ordering, you need to make sure that those columns are ordered correctly. You lose a lot of points in class if you screw that up or overlook it. So, example, we sample 526 students, we record their major, and we ask them how often they read the newspaper. And the options are they never read it, they seldom read it, or they often read it. So first question, is the row mean score test appropriate? Well, we still would have to check the sample size, which we will in the next slide or next couple slides. But it is appropriate, at least in the sense that what? That our explanatory variable is major. I think the options are philosophy, political science, and English. So, right, those are nominal. And our response variable, which is frequency, is ordinal. Seldom is more than never, and often is more than seldom. What scoring should we use? Well, it's not obvious that the difference between never and seldom is the same as the difference between seldom and often, so we should use mod-ridits. So there's our code, data set. Right, notice, so then there's my proc freak, order equals data, and notice I structured the data in such a way that I have never, and then seldom, and then often. So I was very conscious, very deliberate about that. Notice in the table statement, I have scores equals mod-ridit, and then it ran off screen a little bit, but there is also a CMH option. The CMH option I need to actually get my test statistic. And so here it is, right? So there's my table. And there's my test statistic. So my test statistic for the row mean score test is 10.0188. Its p-value is 0.0067. That's less than 0.05. So I would say that, right, I would reject the null hypothesis. At least 2 majors have a different mean amount of reading the newspaper. Looking at that table, right, and focusing on row percents, what do I see? I see that, like, in terms of like row percents, English and political science seem very close to one another, don't they? However, different than both of them seems to be these kind of I don't know, these like lofty philosophy majors. Oh man, right? God bless them. That are able to to transcend the temporal noise that the rest of us are so consumed with, that the rest of us waste all our finite time, reading and reading and reading, gorging ourselves on this like endless stream of newspaper generated nonsense. Not a philosophy major. Right? Their frequency for never is in that 60% rather than 40% for the others. So again, it's kind of unfortunate because we have formulas to compute these means. As near as I can tell, and as much as I've researched, there's not a way to get SAS to actually report the means, which would be very nice, wouldn't it? I mean, it is sort of calculating the means as part of its test statistic. Why not actually report those as descriptive statistics? Now, you can, of course, write like a macro, for example. I have seen some macros written to compute these things, but it's not something that comes out easily from our SAS proc freak output. So often we're kind of left eyeballing it, and eyeballing it, what I would observe is that philosophy majors seem to, on average, read the newspaper less frequently than English and political science majors. Now also, in terms of sample size, all our row totals are over 20, right? 73, 239, 114, all of those numbers are more than 20. We're good, we're golden. Also notice, we don't have to even bother doing that collapsing. All of our cell counts are more than 5, so we don't need to collapse columns to try to get something more than 5. If all of your cell counts are more than 5 and all of your rows are more than 20, then you're fine. Now, if some of your cell counts are less than 5, that's not necessarily bad. Perhaps you could combine the columns in such a way that the new cells do have cell counts more than 5, but in this example, we don't need to do that. All right, so this is just a few slides, again, just kind of putting into writing, committing ourselves to what we had already kind of observed in the output slide. So our null and alternative hypotheses look like this. The average reading newspaper frequency is the same for all 3 majors. The alternative is that at least 2 majors have a different mean newspaper reading frequency. Our sample size is adequate, right? All cell sizes are more than 5, so we don't need to do any of that kind of collapsing nonsense. And all of our row sample sizes are 20 or more. Our test statistic is in the row mean scores differ line, 10.0188. It has 2 degrees of freedom, right? Because we had 3 rows. 3 minus 1 is 2. Its p-value is 0.0067, less than the typical 0.05. Means at least 2 majors have different average reading frequencies. Looking at the table, the most striking difference seems to be philosophy majors read less frequently on average than both political science and English majors. All right, 2 down, check, and just 1 more to go. Let's keep at it. So our third case is what? We have both variables being ordinal. In this situation, we do what's called the correlation test, or right, kind of in a reverse way of describing it, the test of 0 correlation, or test of no correlation. This test exploits, or maybe utilizes is a better word for it, utilizes the ordinality of the rows and the columns to test the hypothesis of no association against one of linear association. The test statistic, its formula is complex. If you look in our textbook, you can see it. It's written in something called a quadratic form. A quadratic form requires this kind of concise way that we haven't really covered in our classes yet. It requires writing our models as like matrices and vectors. It's kind of like a level of abstraction beyond what our program typically goes into, But it is a very, very nice, compact way of writing test statistics and talking about them mathematically. What's kind of cool though is at least when we're under the at least when we're doing integer scoring, the quadratic form simplifies into something like this. It simplifies into a test statistic. So we'll call it Q sub CS, the correlation score test, n minus 1 times r squared, where r actually is that correlation. That correlation we talked about way back in the golden heyday of 512. If we were to actually run proc core, where we assign integer scoring to our categorical variables. Pretty cool, right? Now, it's a little different if instead of integer scoring we're using mod Riddits, but still kind of the same kind of general broad idea. We can think of this as being sort of functionally similar to the correlation that we've talked about in 512. Now, we can show mathematically if our sample size is sufficiently large, then this test statistic follows a chi-square distribution with just one degree of freedom. What do we mean by sufficiently large? Doesn't get any easier than this, right? We want our total sample size to just be 30 or more. That's all we need. Now in this situation, right, what happens when we reject the null hypothesis? When we reject the null hypothesis, that indicates there's significant evidence of a linear relationship. Now our follow-up question becomes, okay, is this a positive or negative linear relationship? Sometimes we can figure this out by eyeballing our table. Alternatively, we can use the measures option and look at the sign of the Pearson correlation statistic. Now, SAS is doing these calculations, these numerical calculations. It can only do numerical calculations on something that's actually categorical. It can only do that if it assigns some sort of weights or scores. So scoring is also an issue. SAS forces us to use the same scoring for both variables. That is, you can't do like integer for the columns and mod Riddits for the rows. So you got to pick one or the other. And so if you have mixed ones, if you think one should be integer and one should be used mod Riddits, well, just like before, when in doubt, mod Riddit it out. We would fall back on mod Riddits. We can get the test statistic and its p-value using the CMH option. Look under the non-zero correlation line. Or actually the chi-square option, if you look at the MH chi-square line. And just like before, if we have ordered categories, now both our rows and columns, make sure that our table has them ordered correctly, because our test statistic is derived from the table. So if the table is ordered wrong, our test statistic will be wrong. All right, so here's an example. We ask 32 teenagers their smoking habits. And by smoking habits, we allow that they never smoke, they sometimes smoke, or they frequently smoke. And we ask them how much they worry about lung cancer. And the options are, who, me, worry? Somewhat worry, or yeah, I'm worried. Is the test of correlation appropriate? Well, sure. We have two variables, both of which are ordered, right? Their smoking habits have an ordinality to it. Some is more than never. Frequent is more than some. And also their amount of worry is ordinal. Somewhat is more than never, and worried is more than somewhat. So a test of correlation is appropriate, right? I think a future slide will ask us about sample size, but we don't even need to look at the table, right? All we need is a sample size that's 30 or more. We have 32 teenagers, so Admittedly, just barely, but just barely is good enough. Our sample size is fine. And then our follow-up question is, what should we do for scoring? Well, in this case, I would say neither of these variables has equal spacing, so we should be using mod ridits. And so there's our code. Notice I'm careful about ordering my data. My smoking frequency is ordered correctly, never, some, and frequent, and my attitudes are ordered correctly, never, somewhat, and worried. I make sure to use the scores equals mod ridit option, as well as everything else needed in my proc freq statement. I guess more specifically the table statement within proc freq. Here's my output. And so if I look at, remember I said that MH chi-square line? If I look at that MH chi-square line, I see 1 degree of freedom, a test statistic of 4.4247, a p-value a little bit less than 0.05. So that means that I reject the null hypothesis. I do think that there is evidence of a linear relationship between smoking frequency and the amount of worry about cancer. I'll let you maybe pause it. Why don't you pause it and look at that table and see if you could think about which direction that's going. As people smoke more, do you think they're worrying more or less about cancer? Try to look at that table and figure it out. I didn't make life easy for us. I probably should have put the row percents in there. I'm not quite sure why I left those out or why I suppressed those. Maybe to make life harder for us, right? We grow through adversity, so maybe, I don't know, maybe I was doing us a favor. Also incidentally, all right, notice that warning. That warning is 89% of the cells have expected counts less than 5. So incidentally, we don't have a sufficient sample size to do a chi-square test. But we do for our test of correlation, right? So that's nice. We're really seeing that this is a good example of where, right, by using the fact, by taking advantage of the fact that both variables are ordered, we're getting away with testing a relationship where if we had to fall back on the Pearson's chi-squared, we just didn't have a large enough sample to do that. Also notice we don't have a large enough sample to do the row means test because, right, our row totals are all less than 20. So no matter how we collapse those columns, we can't get past the fact that the row totals are less than 20. So we have an insufficient sample for a Pearson's, insufficient sample for row means, but pretty cool, right? Because this correlation test requires such a relatively small sample size, we can do that. Here's some follow-up output, right? So the CMH option gives us those values at the bottom. The non-zero correlation line is the same thing, just reported in 2 different places. So that, again, 1 degree of freedom, test statistic, same as before, 4.4247, same p-value. Incidentally, if you had trouble looking at that table and figuring out the direction of the relationship, we can look at the Pearson correlation line and we see negative 0.3778. Negative 0.3778. So a negative correlation. I guess the number's not so important, it's the negative is. So that's saying a negative relationship, which means if we were to look back at that table, it would mean that the more people smoke, the less worried they are about cancer, which seems like a little unintuitive, but I actually think that, again, I think it's real data. And maybe it makes sense, right, if we think about it a little bit more deeply. If you really are worried about cancer, then, right, that worry might motivate you not to smoke. And if you have no worries at all about cancer, well, why not smoke? So we might argue that the ones that smoke should be worried, but perhaps it's not surprising that the reality is that they are not worried. Right? And again, remember, this study is restricted to teenagers who perhaps have a higher sense of immortality than the rest of us. All right, so just a few slides. I think these slides, again, just reiterate what we kind of talked through already. Is our sample size good? Yes, 32 is more than 30. We already observed this, right? We actually would not have a sufficient sample size to do a Pearson's test. The general chi-square test, we also would not have a sufficient sample size to do the rho mean score test. Our null hypothesis is that there's no relationship between smoking frequency and amount of worry over cancer. The alternative is that there is a linear relationship between these. Our test statistic was 4.4247. It had 1 degree of freedom, right? It doesn't matter the size of the table. The test of correlation, no matter how big or small your table, is always just 1 degree of freedom. Our p-value was 0.0354, right? So we reject the null hypothesis. There is evidence of a linear relationship. Try looking at that table again, right? We do see, if you look at that, if you look at the people that never smoked, there is a lot of them, right? It looks like almost 10 out of 15, so like almost 75% are in that worried category. Right, so the people that never smoke, there's a high worry about cancer. And actually that seems to be what's largely maybe driving this thing. It looks like more of a uniform distribution for the other two categories. But if you do go down to those that frequently smoke, there is more of those people, a higher percentage of those people in the what me worry category. So we could kind of see it in the table, but admittedly I think it's easier to see it by just looking at that correlation test statistic and observing that it's negative. Yeah, it appears that the more someone smokes, the less they worry about it. All right, check. So that's all 3 tests. Don't leave just yet. No, don't pack your bags. Don't get up. We still got a little bit of kind of loose ends to wrap up. So let's think about these 3 tests. And let's start with this question. Assume that we had 2 ordinal variables. Maybe like what your class level is, freshman, sophomore, junior, senior, and like some measurement, some like 5-scale measurement of anxiety. Do you think that it's possible for us to fail to reject the correlation test, but reject the rho mean score test, right? Maybe think about that before reading the third bullet point. You're absolutely right. It certainly is possible. When would this happen? This might happen in situations where there's a non-linear relationship. So maybe, for example, right, freshmen are kind of like, they're kind of new to college life, and man, it's like I'm away from my parents, there's a lot going on. Maybe they have a high level of anxiety. By the time you're a sophomore, you've got it figured out. You got a lower level of anxiety. You're a junior, a still low level of anxiety. But now you're a senior, and now it's crunch time. And right, there's a lot of pressure. I got to pass this class. My classes are getting harder. I got to start thinking about, man, I got to get a job after I graduate. Right now, that anxiety level rises again. Something like this would probably have a non-significant test of correlation, which means we want to be a little bit careful with how we apply all these different tests, right? It might be tempting to just say like, okay, both my variables are ordinal. I'm just going to take a look at this correlation line. This correlation line is not significant, and so there's nothing going on. That's not necessarily true. if you have ordinal variables, you could use all three tests. You just have to be cognizant that all three of those are testing slightly different things, right? In this situation, the correlation test would be non-significant, but the row mean test would probably be significant. And it would, and through that, we might be able to catch this perhaps interesting phenomenon that we just observed, or that we just speculated on. So, keep in mind, when you have two ordinal variables, all three tests are justifiable. Just keep in mind that each is testing a slightly different alternative hypothesis. And the correlation test has less stringent sample size requirements. So it might be that our sample is so small we can only get away with the correlation test. But if we have a large enough sample, we're justified in doing all three. Similarly, if we have one ordinal and one nominal, we can use both the row mean score test and the test of general association. Now, if you only have two nominal variables, all you can do is the test of general association. Now, incidentally, I believe we already made the statement, but we can look at it and maybe think about it with a little bit more depth. I made the statement that each test becomes progressively more powerful. We can actually see that fact through the fact that their degrees of freedom are decreasing. Right? We go from S minus 1 times R minus 1 to S minus 1 to just 1. Right? As we move through these tests, the degrees of freedom are going down. And it's a stats fact that if you have two chi-square statistics that have the exact same value, but one has smaller degrees of freedom, the one with smaller degrees of freedom has the smaller p-value. Right? That's how we're getting that increased power. In fact, incidentally, right, if you go back to that thing, and I know we didn't have a large enough sample size, but if you go back and take a look at the smoking example we just did, you will see the correlation test rejects, whereas the other two fail to reject, right? The correlation test has more power. Now, the last thing I want to talk about is three special cases of what we've discussed, right? So we just talked about this S by R table, right, from arbitrarily large table. Let's look at what happens in the situations where we have a 2 by 2 table, a 2 by R. So what would that be? A 2 by R would be a kind of short but stout table, and an S by 2 would be like a tall and skinny table. So we actually saw, I think, last class, in a 2 by 2 table, all three tests are equivalent. All right, it's kind of like they're all just like a degenerate form of one another. There's not a lot going on. Testing whether the probabilities are the same is testing whether the means are the same as testing whether or not there's a linear relationship. You could also incidentally see it just in terms of degrees of freedom, right? In a 2 by 2 table, S minus 1 times R minus 1 is the same as S minus 1, which is the same as 1. Right? All those degrees of freedom formula all end up equating to 1. In a 2 by R table, this is in the situation where the columns are unordered. Well, now we just simply have a test of general association. And when they are ordered, we can technically use the row mean test. However, in this instance, the row mean score test and the test of correlation are actually the same. So I'll let you think about that a little bit. You should be able to see that certainly the degrees of freedom match, right? So if it's 2 by R, the degrees of freedom for the row mean score test is just 2 minus 1, which is 1. And the test of correlation has 1 degree of freedom. Right? If we only have two rows, we only have two means that we're comparing. So, right, it has to be that one mean is more or less than the other, right? Which is kind of like a degenerate increasing or decreasing relationship. In an S by 2 situation, where the rows are unordered, this is just a test of general association. But when the rows are ordered, we can do a test of correlation. And a test of correlation is doing what? Even right, no matter what's going on with our columns, we can still get away with a test of correlation. Because what's the test of correlation doing? The test of correlation is really just looking at like whether or not there's a trend in proportions, right? So like imagine that we have a situation, I don't know, maybe our rows are class level again, right? Freshman, sophomore, junior, senior. And maybe it's just I don't know, do you like chocolate ice cream? We've been doing all these depressing examples. Let's talk about something more cheerful, like ice cream or Captain Crunch. Do you like delicious breakfast cereal? And they say yes or no. We typically would not think of yes or no as like an ordinal variable. But in this situation, we actually can do a test of correlation. And what that test of correlation is essentially doing, it's basically looking at what percent of freshmen like breakfast cereal, what percentage of sophomores like breakfast cereal, what percentage of juniors like breakfast cereal, and what percentage of seniors. And it's looking at whether or not these percentages are increasing or decreasing in a linear fashion. That's essentially what's going on computationally or mathematically.